So I'm Cliff Click. I've been in this game for a long time. I've been coding for like 45 years. Fell in love with it way back in the day when, I guess my first machine had 256 bytes of memory, not kilobytes, megabytes, gigabytes, no, bytes. And of course, it was all machine code, hand twiddled, whatever kinds of stuff. And it was always a tool builder all my life. And so sort of over time, as I got more and more skilled at tool building, I participated in bigger and bigger projects, eventually doing all kinds of stuff with the Java virtual machine when Sun pulled me in, a long time ago, 2000 something or another, 1997, I guess. And at that time, I had already done a number of compilers, and I was brought in to do the core JIT compiler and the hotspot virtual machine, and ended up working on Java virtual machines for about 15 years. Now, I'm about 10 years out of date from the standard Oracle JVM, so some stuff I'm going to present today is old. Most of it's still spot on. And so there's a bunch of interesting things that go into JVM that we're going to cover today. And in particular, we're going to talk about stuff that was like really cool and stuff that's sort of like, what the hell is that doing? And maybe figure out that we could do a better job for a lot of these things. So there's tons of stuff in a JVM, and many of the things that are in there were just sort of volunteered by a naive change in specs. Somebody, bright idea, said, hey, finalizers, they're a fantastic idea, and that turned out to be a total nightmare. So what's in a JVM? There's this high-quality garbage collection. At the time that I started, GC was well-known academically. No one was using it in production. Java changed that. It's so much easier to use than malloc and free that it just changed how the world thinks about coding in that way. When the first GCs came out, of course, they were very expensive. They're still better than malloc and free, but there was some heavy costs. These days, it's much better. I had a direct responsibility for this piece, high-quality machine code generation. These days, there's multiple JITs. The JIT was a term that came along, actually, after I started, just in time. Doesn't say anything about compilation, so you could apply to lots of things. But in this case, it means compilation, code management, profiling the code into what's hot and what's not, building a byte code cost model. I'll talk more about that in a minute. There's this uniform threading and memory models. One of the big things that Java brought to the programming world was the ability to think about how different threads talked through a shared memory machine. And up to that time, it was all very ad hoc. And so it was very difficult to write multi-core, multi-threaded software that would actually work in more than just the machine in your hand. And Java changed that. And of course, brought type safety, range check safety, array bounds overrun fixes, and all that kind of stuff. Buried in there is also dynamic class loading. You can load code after the program is run, and the code you load works just as well as the original code. So it's not the old C model where it's a closed world. You have to have all your code at once. You can add code later, which is all the big web servers all load code and execute, load code and execute. But it's also the case that the loaded code gets the same optimizations and the same performance as the original code. So programs can be built incrementally over time instead of having to become all at once or pay a penalty to be later. It's just the same either way. There's high-quality time access. This sounds like it's going to be really easy to do. Turns out it's really hard to do and had not been done well. And I'll talk more about that when we get there. And then there's all kinds of other services, JVM, TI, PI, DI, JNI, reflection. Of course, the Java library, the JDK. Access to the OS. And when I say access to the OS, I mean, yes, threads, scheduling, priorities, but yes, in a best possible way. If your machine supports 1,000 cores, and I worked on a machine that did that, then Java will let you run a 1,000-core program well. So it's not just that it's there well. It works well, it's robust, it's efficient, it's fast, it's good, it's all these things. So I'm going to point this way and it works. There it goes. So where did all this come from? Well, it was mostly incrementally added over time. The language, the VM itself, and the hardware, they all co-evolved. So for instance, I started before there were 64-bit machines. So 64 bits came along later, and it was added to the system. 64-bit pointers. Long math was done by adding a high and a low on an integers, 2 pieces, and then with an add and add with carry, which meant it wasn't atomic to load or store longs. And there's still in the spec a thing that says if you load or store a long, you might get word shearing, which doesn't happen anymore, but back then you did. I started on a single core machine. At some point, I got a dual core, like compact dual core machine. It had 2. It was a big step up. Make it work with 2 instead of 1. It turns out that's a huge problem. Then there was a Dell dual core machine, and the memory models between the 2 different machines was different because the motherboard determined the communication patterns between the cores, and Dell and Compact didn't have a discussion about how they should communicate. And so the Java memory model eventually showed up because everyone's hardware was different. So why do we have all these things? Because they give you an illusion that as a Java programmer, you can go work over without needing to deal with what goes underneath the hood, right? It's the V in Java virtual machine. It's virtual. It's this great abstraction pattern. You get to add value elsewhere, and you can rely on the JVM provide these services. And so it's very similar like an x86. How many people here work on x86 chips themselves, like transistor level? But you use them every day. So Intel provides a service of an x86, and you don't have to think about it. You just use it, and you provide value above it. Same with the virtual machine. Java programmers add value above. Java virtual machine engineers put the value between the x86 and the VM. Okay, so enough of that. What are all these services? And where do they come from? Why are they there? Some are unique, but many of them actually overlap with existing OS services. And it turns out that the OS didn't do the exact thing that Java wanted, and so the service didn't work the way you expected, and so Java had to replicate that service or have to suffer with various kind of penalties. We'll talk about more of that in a minute here. We'll get there. So what I'm going to go do now, actually I'm going to stop for a second here. How am I doing in terms of speaking? Because I'm a native English speaker. I get excited. I talk fast. I suspect, okay, I got 1 thumbs up, a couple thumbs up. Okay, fine. All right, fair enough. So now let's talk about illusions that we have. So infinite memory. We have this illusion of infinite memory. Garbage collection, right? You just say new, and you get some memory, and you new, and you new, and you new, and you do it endlessly, and you always get new memory. And of course, some stuff dies, but you don't track the lifetime. Garbage collection does that. And the garbage collection keeps returning you the memory that you're not using, and you can turn around and use new again. So much easier to use than malloc and free. This was the paradigm before the Java came along. Fewer bugs, quicker time to market. It turns out that it enables certain kinds of concurrent algorithms that you simply cannot do with malloc and free because tracking the lifetimes of things with malloc and free is simply not feasible. I don't have an example. I see some confused looks. I can give examples maybe later, but there are definitely algorithms that don't work without a garbage collector. You will run out of memory because you can't track the lifetimes concurrently. Fine. GC, so the slide is getting old, so maybe 2 decades ago to the last decade or the last 15 to 5 years ago, they went from being it worked and it was good enough to being it's like hugely the obvious thing to do. So they're robust, parallel, concurrent, incremental generally, still this major user pain point for large JVMs, too many tuning things. There are whole companies whose entire job it is to tune garbage collection for big servers. Lots of different vendors doing work here. You maybe get 30% variation in throughput. That's actually a pretty big number. Pause times can vary by 6 orders of magnitude. So stock GC on a tens of gigabytes of heap might give you pauses occasionally in the order of 10 full seconds. That would be a full GC pause. Whereas Azul, I know there's an active Azul office here, hundreds of gigabytes with, it used to be milliseconds now. I believe it's down in the microsecond range. The actual max pause time. This is actively in use by high-frequency traders. right? They have two ways they go. One is they have a giant heap. They don't allocate after the start of the world, and at the end of the trading day, they shut the machine off, never a GC cycle. And the other way they do it is they use an Azul collector. And however, okay, fine. And then IBM got there first with their metronome collector, but it wasn't able to handle the magnitude that Azul's is. Azul's will handle terabytes of heap. Well, you don't get very many terabytes on one machine, but hundreds of gigabytes definitely. So it's a nice thing going on there. So byte codes. This is the illusion that the byte codes are fast. Turns out, of course, byte codes themselves are this lousy way to describe program semantics. A lot better ways to talk about program semantics, but we have byte codes. We're kind of stuck, so we have to deal with it. The main win is that it hides the CPU details. You talk about your program and the program meaning and semantics, what it's supposed to do, and you don't worry about how many registers you have and what an add or a store looks like. That's all done by the JIT. You expect them to be fast, but of course, if you interpret, they're slow, because they do all kinds of weird, bizarre things, and you get the expected cost model by compiling, right? So you eventually JIT the byte codes to machine code, and you get this high-quality optimizing compiler. So I'll tell people it's roughly GCC-02. It's the rough equivalent of the second-tier optimization on a standard good C compiler. Why didn't I use a standard good C compiler back in the day? Because it didn't do the things I needed. It didn't track pointers, garbage collected pointers. They would get lost in the compiler. You couldn't figure out what was garbage collected pointer and what wasn't afterwards. And then the GC couldn't update the pointers, so you couldn't move things. It didn't honor the memory model. Didn't have any clue what a memory model was or any way to go add or deal with what ordering is allowed and what isn't. In particular, register allocators on these C compilers would be very aggressive about reordering loads and stores as part of the register allocation process in ways that wouldn't match the memory model. So I needed to have a register allocator honor the memory model. And then there were a lot of new code patterns to optimize. So Java came with this type safety notion. You didn't get a null pointer exception as a crash and burn behavior. You got it as this nice stack trace, an exception, Java exception gets thrown. People think, well, that's the crash. No, back in the day, a null pointer exception in a C program like halted your program as a halt and catch fire, right? Program stopped and went to the OS and was dead. Now you could catch it at least and see what happened. Maybe get a clean stack trace, maybe get the debugger to get involved. You could do all kinds of fun stuff. To do that, you had to have null pointer handling done correctly. It was an optimization that didn't exist for the C compilers because they just didn't care. Same for range check elimination. You ran off the end of a buffer. Well, these days you get a security hole that makes the internet news and everyone's all, up in arms about it. Back in the day, you ran off the end of the buffer and the program kind of got sick and sicker and sicker and eventually crashed. In Java, you get a range check bug that you then catch in the debugger, and then you fix your bug and your bug goes away and your problem's solved. But that means you run with range check testing all the time, which means that every array access would be slowed down by 5 to 10x for a range check per every array access, unless you optimize it. So you optimized them. But the C compilers didn't, so I had to have new things to optimize. There were a bunch of other stuff I had to optimize here. Class hierarchy analysis and loading, so I guess we'll get there in a second. Another thing that came out of this was that JITting was done at the runtime. It wasn't done ahead of time, which meant that you're compiling while your program ran, which meant that you were both running interpreted for a while because you hadn't compiled yet, and then you had to pick something to go compile, and that required you to profile because you didn't have time to go JIT everything. But if you profile, you get better code than non-profiled code because you get to make a bunch of intelligent decisions that a C compiler never gets to do because it doesn't have any profiling data. So you get to inline what's hot, you get to know where to focus like big loop optimizations, loop unrolling and range check elimination around loops, branch prediction, code generation, scheduling, a bunch of stuff. Turns out that I was a C compiler guy long before I did the JIT in Java, and profiled code is worth 10 to 20% more speed in the land of C over Java, but you never profiled in C code because it was too much pain in the neck. You had to run your program once with the valid live data set to decide what to collect a profile, and then you had to recompile and then run it again. And the C compiler guys did it for the hardware, for the benchmarks, but no one else ever did. Whereas in the land of Java, you get it all the time. And that gives you some speed up that you don't ever get out of the C compilers. There's a counter side to that, of course, is that because you're doing it on the fly, you have to be fast, you skip some very expensive optimizations. And I'll claim that the code generation that comes out is roughly on par with GCC-02. It's a little better because you can profile, a little worse because you can't do the really expensive optimizations, a little better because you have some focus in the right direction, a little worse because you don't have the whole program all at once in front of you to do some stuff there. So it kind of balances out. Okay, virtual calls. In the land of C++, there was this thing called a virtual calls, part of object-oriented programming. It's a great concept. But that involves, in the hardware, an instruction called a jump register, which is about 30 times slower than a standard call instruction. Depends on your x86 version number, but that's called about 30 times. Plus, there's generally some dependent loads in front. It stacks up 40 or 50 clock cycles, as opposed to one over a standard static call. And Java said everything's virtual by default unless you said final. Well, if it's all virtual by default and everything's 50 times slower for being virtual, that would suck. So we have to do something about it. So we optimize. So you start by doing class hierarchy analysis, and that's just where you say, I have this virtual call on a class. Is that method overridden by any subclass? And the answer is typically no, it's not, and therefore you can make a static call out of it. So most virtual calls become static right there. But you have to watch the class hierarchy. And if a new class comes along where you had said you were not overridden and you coded the code that way, now when the new class shows up, you are overridden and you have to go recompile. So you may have to rejet things. You may have to stop with a running code, break it back down to the interpreter, reprofile, rejet, re-inline decisions. All things are new and recompile. CHA can also fail, claiming there are, in fact, multiple subclasses. But it turns out, in the standard way that Java's run, most call sites that would otherwise be virtual have really only one target method at runtime. So it's this funny bimodal distribution. 95% of what would be a virtual call go to one method for the life of the program. And 5%, the remaining 5%, go to 10 to 20 methods. They go megamorphic. They go to a lot of targets. So if you land in the 95% case, you can use an inline cache. And what is an inline cache? It's a little tiny one entry cache. It has a key and a value. The key is the class. The value is the target method. It's coded directly in the code. It's patched at runtime, where you patch in the key and you patch in the target method, and you patch in the target method by patching the call instruction directly in the x86 hardware or ARM or whatever your chip is. And so the effect is you load the object header, you compare against the class ID as a constant in the code, and you make a static call to the target, which an x86 will do these 3 instructions in one clock cycle. So it brings back the performance of a static call for the 95% case. And in the 5% case where that's not true, you fall back to doing a classic C++ style virtual call, the same as the C++ guys would do anyhow, which is you load, 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 jump register, and it's slow, but they're not very common anymore. Partial programs are fast. I talked a little bit about this earlier. You get this, class loading comes along late in life. You call class for name. And you have a new piece of code that you didn't have before. And how fast is it? How does it run? Well, it starts interpreted, but after a while it jits, and the performance becomes just as good as the original program. So partial programs are as fast as whole programs, and that's one of the key things that comes with a JVM. So you can add new parts. Big web server, somebody has a web request come in, they load J2E, whatever, they load some code, and you execute it. And you load code, and you execute it. So eventually, you have to de-optimize because some of your assumptions about how you compiled the code are no longer correct because new classes loaded in. And that means you have to do this de-optimization, reprofile, rejet. De-optimization is a kind of a hard problem. It's not rocket science, but there are a hell of a lot of details to make that one go, so make it work right. But once you get it, you can do this magic trick of adding code and optimizing it as if there will never be another subclass, like you have the whole program in front of you, but when later you discover more program code, you can correct and go on. Memory models. All the machines have a different memory model, and the rules on visibility of loads and stores between cores just vary from machine to machine to machine. Within generations of the same machine, x86 is very conservative, and of course I started at Sun, so I had to do Spark, was conservative, but IBM did Power, and MIPS and very much ARM are very less conservative. They would allow reorderings of loads and stores, right? The Azul hardware, very aggressive. Itanium, fortunately dead now, thank you very much, very aggressive. So your program semantics would depend on what the memory model is. So if the hardware doesn't match the memory model, your program semantics depend on the hardware you have. You write a multi-threaded program, back in the day, it ran on Dell motherboard, but not on a compact motherboard because the communication patterns across the motherboard were different. The Java virtual machine fixes that. None of the hardware out there matches the Java memory model, so you must bridge the gap. But you have to do it in a way that keeps normal loads and stores fast. You can't have this huge cost. You can't fence at every load or store, right? An easy answer, do a memory fence at every load and store, slow you down by 10x. Can't do it. So you have to have combinations of fences only where necessary, code scheduling, placement of your locks and your CAS. People know what a CAS is when I say CAS? Compare and swap. It's the unit of atomic updates, the only atomic instruction in any piece of modern hardware. IBM has like load, link, store, conditional does the same kind of thing. But that's it. You have this one magical instruction that guarantees you an atomic update and a memory word, even if other people are all banging on the same word, one guy will win, and you'll know who won. Okay. It's necessary for all locks, for instance. It's the key piece that makes a lock work. So with needing close cooperation from the JIT, can't reschedule across the locking boundary or you lose the properties of a lock. You can't let the hardware reschedule across a locking boundary, which on some hardware you need a fence, and some hardware you don't, and some hardware you need a fence on the lock but not the unlock, and some you need it the other way around, some you need it both, whatever. Requires detailed hardware knowledge as part of baked into the JIT. And then, of course, the threading model. You get this consistent threading model, even though Linux and Solaris and, say, AIX and, say, Windows have these different threading models. And it's going to work on a cell phone, but also on my 1,000-core machine. And I just, synchronized, wait, notify, join. These all just work. And that's part of the magic of the JVMs. Baked into it is how to deal with concurrency and threading models in a way that you can expose it to the Java programmers in a way we all understand. But under the hood, there's something different going on in each of the different OSs. And then I talked about it, so locks. Locks are fast. And in fact, they're very fast. And they were highly optimized because the synchronized keyword becomes so common. So the contended locks obviously block and go into the OS. And you'd like to say fairness from the OS, and in fact, you don't get it from the OS. But uncontended locks are, these days, a dozen nanoseconds or so, and could be even faster if biased locking is working. So there's a lot of effort to make locks work, and I'll talk more about that in some of the other talks I'm giving later in the week. I guess we'll go on here. So what happened here is people don't know how to program concurrently. And I'll claim even today, we have some ideas of how to do concurrent programming, but mostly there's a lot of experimentation. Hey, let's try Erlang. Let's try actors. Let's try Java's threads and locks. Well, we understand that model pretty well. We understand it's not very great. Maybe there's a better way. Maybe go to J2EE has beans, right? There's some sort of concurrent thing that you can define in there. So you get this, I don't know what the hell I'm doing thing. And so in the case of, especially for Java, so threads and locking, you get race conditions, bugs. They only happen rarely under heavy load in the hard to find places. So you add a lock to try to make the bug go away. You can't ever reproduce it on your desktop. It only fails in production under heavy load, and you add another lock, and you add another lock, and you add another lock until the locks become really common, and eventually you get the bugs beaten out. And it's some sort of lowest common denominator programming style. I don't understand the concurrency I have, so I keep adding locks until it works. So we had to optimize them. And you get this very particular concurrent programming style. Thread pools and work lists over shared caches is very common. And we learned a lot about concurrent programming as an industry, and we understand that there's a model we all understand, but also this cannot be the best way to do concurrent programming. There has to be a better way. There are a lot of folks trying to find that better way. Fast time access. So along with, speed of locks, time is the other one that everyone cares about. We only have so much on the planet, and then our time is done. So we're all crucially interested in time. And in the case of Java, you call current time millis, right? Okay, fine. On some big benchmarks that were important back in the day, it would be called billions of times a second. So if you do the math on billions of times a second, that's actually really hard to do. But you get a big shared memory concurrent server, you can call it that fast. But it's actually common in all large Java apps. And then you have this funny eye chart in the middle here. What's this say? Well, it says if thread 1 does a current time millis, and it's a number that's less than thread 2's current time millis, then thread 1 will expect that he has a happens before relationship to thread 2 on the clock cycle. That is to say, if I have a number for the current time millis that differs from your number by 1 millisecond, they actually will assume that they differ by even on the clock cycle boundary, not just the millisecond, but the clock cycle. And if you fail to keep that correct, real programs will crash. Big, complicated web servers of various kinds, and I would say 3 out of the 4 big ones I tried back in the day will crash if you fail this observation. So this makes it really hard to compute time that's consistent across multiple cores to the clock cycle, right? So, hey, x86 came along and said, I have this tick counting register, TSC, that updates once a clock cycle, except that it's not coherent across my CPUs, and it ticks faster or slower, for instance, because one core goes into low power mode, maybe because it got too hot, because it had to thermal throttle it. So it wasn't consistent, and if they always switched you from core to core, your current time millis number would go backwards. So that was really a bug. It was not monotonically increasing per CPU. It was per CPU, but not per thread. There's another thing hit here. So we switched from TSC register to the Linux get time of day call, which is this mostly user mode atomic struct read, which was like, read these 4 or 5 things out of memory, compute current time millis, go read these 4 or 5 things again, and if they didn't change, you assume you got an atomic read and you have a valid result. But if they change because the OS stomped some numbers and you got half of a read while he was stomping numbers in, then you had to go recompute. So you spun until you got an atomic read of 5 values, and then you got a current time millis out. For a thing that you're calling billion times a second, you have to do like 100 clocks worth of work. Seems like a pain in the neck. There's a better way, and that's just to have a plain load updated by the OS in a private page that just stamps a new current time millis 1,000 times a second. And a load instruction will be atomic and give it you on the clock cycle boundary, be correct. 10% speed boost on a key benchmark. Back in the day, there was a flag, -XX:+ aggressive optimizations that switched from using this to the TSC register, which was not legal except on this benchmark. Wasn't proud of it, but I got told, go do this thing. Meanwhile, hypervisors came along, and they had this cool idea that they'll go idealize the TSC register, which means that they'll intercept a call to the TSC, and they'll make it uniform, monotonically ticking upwards, coherent across your cores. It's great. It's also 100 times slower. Okay, so here I think I'm calling 1 billion times a second. It gets 100 times slower. This is like really bad for your benchmarks. So this was like a loser too. Like, cool idea, bros, but no. Okay. So that's sort of things that are in a JVM that we know are in there and work well. So let me look at some things that we think we have, we don't really, or that we wish we had. Tail calls, infinite stack, the illusion of an infinite stack. A whole lot of people in the functional programming language community would love to have tail calls be in there. Back in the day when I was at Sun, I estimated about 2 weeks worth of work. I could have thrown it in. It just never came to the top of my queue of things to go do before I left. So we still, 15 years later, don't have tail calls. That means some functional languages, which otherwise would do looping over large structures via recursive calls, can't do it. They have to do tail call elimination themselves instead of having the JVM do it. Writing code as data. We're getting close. It was a long time before we got Lambda 8 thunks. It was a decade of Java didn't have thunks. Those aren't real closures, but they're kind of close. Close enough for, horseshoes and hand grenades and thermonuclear devices, right? Yeah, okay, fine. Maybe we can claim we can have that one. How about big integer is cheap as little integer? It never will be. And this is auto-boxing, right? So I can't put a little int into a hash table as the key, but it auto-boxes for me. This is great, right? Well, it turns out that the auto-boxing requires you to do a memory allocation and of a final field, which requires a fencing, a scheduling fence. x86 doesn't need an actual piece of hardware fence, but it needs to have a scheduling fence. The compiler has to have a fence there. Also, when you do that allocation, it's guaranteed a cache miss, because that new that you do is never been in the processor's core memory since the last full GC cycle. So 100% chance of a full cache miss, plus a scheduling barrier in the compiler, plus some allocation. Auto-boxing's not actually free. And if you do it by accident in hot code, you can lose here. So I do a class where I give a demo of memory bandwidth over big arrays of data. So a couple of gigabytes I'm going to load from disk. I'm going to do a bunch of math on it. Every allocation that you do in the inner loop of the big read my 2 gigs and do some math slows you down by this enormous factor. And I get giant speedups by getting rid of allocations that are hidden from you. One of them is this. Don't do this by accident in your hot loop, or you'll pay an allocation cost that looks free, doesn't show up on any profile, and will cost you 5x, 10x slowdowns. Big numbers. And of course, big integer math. Fortunately, I think here we've kind of agreed that you don't overflow 64 bits unless you know that you're likely to overflow 64 bits, and then it's a pay-as-you-go kind of thing. I think I'm going to overflow 64 bits, so I'm going to use big integer, but I know that's expensive, but I know it's OK here, so I made an intelligent decision. It's OK to be slow on this particular math because I want the big integer. Atomic multi-address update. So we talked about locks and Java threads a whole lot. They have all these complicated issues, these data race bugs that are hard to diagnose. For a long time, people talked about having transactional memory updates, software transactional memory updates. I think one of my talks coming up later this week will be on the Azul's hardware transactional memory and why transactional memory doesn't actually work. It does, technically. It does not help you run code fast, concurrently, parallel, sort of without thinking about it. It was a great academic concept that failed in practice. Fast alternative call bindings, they finally showed up a couple years ago as an invoke dynamic. So this was, Groovy, JRuby, Jython, J whatever. People who weren't Java, running on a JVM, didn't have the Java semantics for a call. They had their own semantics. The lookups were different. They still wanted that fast inline cache thing. Inline caches do this magic trick where you usually go to the same target. This is true for many, many languages, but the rules and what that target should be differ from Java versus JavaScript versus JRuby or whatever. And because they're different, you can't use an inline cache as the JVM does. But the same concept should work, and that's what invoke dynamic lets happen. So that brings in some of the goodness of inline caches to these sort of non-Java languages. OK. Another illusion, Oracle's hard at it, but I'll claim that the code base has not moved very fast for a very long time. Very slow new feature rate of change, right? Because the code is now closer to 25 years old. Large chunks of the code are very fragile. I know for a fact that people are scared to death of touching the register allocator, for instance, right? So they rewrite from scratch, but they won't touch the existing register allocator. They won't touch the code management either for the same reason. Azul systems, I rewrote giant chunks of major subsystems, 100,000 diffs easily from the OpenJDK. As a consequence, got something that was a lot simpler, a lot faster, a lot lighter, a lot easier to move. That turned into low latency GC, the Azul's fantastic GC, which is still better than anything Oracle's got right now by a fair amount. Because ZGC is coming along, and basically it's the Azul collector done on an Oracle JVM. That was all enabled by doing major rewrites that Oracle would do well to do. Thread priorities. Wow, we'd love to have thread priorities. How many people think we actually have thread priorities in a JVM? Right? So yeah, it looks like it's in the spec, right? Okay, what really happens is that on Linux, every thread runs at the max priority unless you're root. Of course, you're not going to run this thing as root permission on Linux in your production. And it's also relative to the entire machine, not just the one process. So you can have a low priority JVM doing some background bulk work. It'll have some high priority threads, and say concurrent GC threads trying to keep up. But some other JVM, which in theory is higher priority, like serving web pages to an active customer who want to buy something, will get starved out. I'll talk more about that in a minute, but there is an issue with thread priorities that they don't actually work as stated. We need thread priorities within a JVM and then from process to process as well, and that's an OS issue. Write once, run anywhere almost works. It's very close, but scale matters. Things you can do on very small programs and very large programs are different, and you have to think about things differently. In particular, big data set, whatever kinds of thinking requires you to ponder your program's semantics in a way that you don't have to deal with when you're looking at very small stuff. Finalizers. Finalizers are useful. Turns out that they suck for what they were intended to be useful for. So, and that's because there's no timeliness guarantees. A finalizer happens when the GC gets around to it, right? And the code eventually runs, but eventually can be, never. And so my classic example here is an early version of Tomcat, which is this nice web server, Apache web server, okay? Would have a file handle that was put on a Java object, and when the object went dead, they would close the file handle, and you would reclaim the file handle. Well, of course, in the beginning, Java heaps were small, and so full GC cycles happened a lot. Because they happened a lot, you got your file handles back fast. Because the heaps were small, the full GC was cheap. But the hardware was kind of expensive, and you got new hardware with more and more memory, so people kept making one web server handle more and more load because you could put more memory on it and more cores, and it would run faster. And except that full GC cycles now took longer to come around because you had more memory. So eventually they came so slow between full GC cycles that you didn't reclaim them before you ran out of file handles. So the web server wouldn't have a file handle. He was going to open one for every web request, and it would open at some steady, fast rate until he'd run out. So there was a scream and a big to-do, and I got told to go put a hook back in from the OS file handle call back into the JVM, so that when you ran out of file handles in the JVM, you called into the garbage collector and said, please, Mr. GC, run an emergency GC cycle right now, running all possible file handles, or finalizers. Okay. When that was done, you went back and you tried again to get another file handle, right? And so what really happened here is we're managing an OS resource which requires a GC trigger to go happen. And full GC cycles got expensive on those machines because that was the classic old school collector, but that was how you got your file handles back. So that rescued Tomcat, except you have to do the same thing for network byte buffers. You have to do the same thing for graphics buffers, for doing video games, for doing anything that has an OS managed resource. This is not the right way to do this. You need to have some smarts about what you're doing when you're having an OS resource. You have timeliness guarantees. So ref counting, if you have to go that way, some sort of stack-oriented behavior where I start a web request, and when I exit that web request, I return the file handle then, right? Some lexical scoping, something, but not having a GC try to manage your file handles. Here's another more interesting one, soft and phantom refs. Again, this is using GC to manage a user resource. The cache. The cache holds on to all kinds of stuff in the hopes that somebody will use it eventually. But the box runs out of memory when it runs a while because so many things have happened and got cached that the cache is full of stuff that no one's touched in a long time. I want to get rid of that. So I'll use the garbage collector to say, hey, I'm low on memory, clean it out of my cache. So you have this soft ref that eventually becomes the GC is allowed to null it out and reclaim the memory. But what happens is your server is running along and you've added load and you got your caches and your load is high, but it's working well because the caches are full and things are hitting in the cache. And so while the load is like this, you're running fine. You get a little more load, you get a little GC cycle, and you bump up. You got out of memory, you run a GC cycle, and you throw some things out of your cache. Okay, now you have some things out of your cache. The same load's still there. It goes and probes the cache. Well, now it misses because it's not in the cache. Because it misses, you have to go rebuild it. Well, rebuilding is a lot of work and uses a lot of memory. So you allocate a bunch of memory to go fill the thing you just missed in the cache, and you run out of memory again because you were already near the edge of your load limit. And because you GC'd again, the GC got more aggressive and emptied your cache more. Now you miss even more. Because you're missing more, the GC runs out of memory because you're doing all the hard work to fill the cache, and the GC flushes your cache again, and you get in this vicious cycle where you're constantly doing all the work, your cache is endlessly empty. Every time it might fill up, the GC cycle runs and wipes the cache clean, and you don't have a cache anymore, and your server throughput falls off by an order of magnitude because you don't have a cache. And if you stop the load, the GC will quit panicking and catch up. And then you can add the load a little bit at a time, and the cache will fill in, and you can add the load, and the cache will work, and you'll get to the same high throughput. But when you crash that performance curve, it never comes back until you kill the load. Usually at this point, people, I don't understand what's happening, it's in the CGC, and I'm fucked, and they just reboot the server, right? But I've seen this plenty, and eventually, deduced it down to this. So there is a negative feedback cycle using soft refs on a busy machine. And what really happens here is that the GC has no clue what your cache is, or that it is a cache, or what the least recently used, or what a good caching policy is. Because it doesn't have a clue, it does a dumb thing with a cache. Whereas if I had a smart caching policy, I might go do least recently used. Throw out this stuff that hasn't seen the light of day in forever, and only keep the stuff that's currently being touched by folks, right? And that would let it work. But as it stands, the GC is just clueless about your program's higher level meaning. He just throws things out willy-nilly, caching or not. And in fact, some of these things here, where the GC would flush a soft ref, we found all kinds of bugs where the program just assumed that if I did a put into a cache with a soft ref, the next instruction would be a get, it would hit. But no, if a GC cycle ran in between the put and the get, it would not hit, it would be null. And they would take null pointer exceptions and die. So this was, it's not a useful way to think about how to manage your caches. Okay. So I'm going to sort it out. What time is it? How bad? Okay, fine. We'll wind it down pretty quick here. So what do we got? Services that the JVM provides. Garbage collection, that's a big one. JITting, that's a big one. Java memory management, that's a big one. Thread management, fast time access, hiding the CPU details and the hardware from you so you don't have to think about it. You have a sensible model of what looks like something you can execute on any piece of hardware, but in fact, you have to do all this magic shit to make it work on any piece of hardware. There's a bunch of services provided below the JVM, like threads and context switching, thread priorities, IOs, and files that come through the JVM in a useful way, that the JVM just wraps them up and hands them to you, but in a high throughput, highly robust, easy to access kind of way. And then there's lots of things people do with JVMs that are common, that they build on top of a JVM, but these days you grab libraries to do them, but they are definitely very commonly used. So thread pools as a concurrent programming style. Thread pools and work lists, task lists, transactions, crypto, caching, database caching, web service caching, all kinds of caching things. Various alternative models of concurrent programming, new dispatching rules, big integer math as part of the default programming model I'm talking about, all these kinds of things. So some stuff that I claim that we could do better with. Fast, quality time, should be an OS service. You get it out of the JVM, but it was really hard to do, and it's not as fast as you could get. It's the best we get here is quality, not fast, from OS get time of day, 100 clock cycles to get current time millis, because of the requirement to be clock cycle accurate between threads. But this could be done in 1 clock or less with a memory word that was updated by the OS, by the kernel. That's just a read-only page that has a current time millis in the page. You just read it by anybody. It's a process shared page, and that would give you a clock cycle accurate 1 clock current time millis. Thread priorities. OS gives you thread priorities at the process level, but that means and high priority JVM should starve lower priority ones. That's what you have OS priorities for. But JVM needs thread priorities within a process. In particular, if you have a concurrent GC, that GC needs to have cycles to run, or a fast-running mutator will run out of memory, and you'll take the GC pause you're trying to avoid. You have to have enough cycles on the concurrent GC, or it actually is not concurrent, right? Same thing for JITting. If you have 1,000 runnable threads, and yes, this benchmark actually happened to me, you have 1,000 runnable threads, they all run, 1/1000th of them is the JIT thread, he doesn't get enough time to JIT any code, and the program just runs interpreted always, because the JIT never runs, right? So the JIT needs to have a higher priority thread than the mutators, or you won't get any code JITted. So we ended up faking thread priorities at Azul with a duty-style locks and blocks, because we wanted to do a low pause concurrent collector, and you absolutely had to have some sort of thread priorities that worked to make a low pause collector work. The low pause collector had to have his cycles in there, right? I claim this belongs in the OS. Like, what the hell are we doing, locks and blocks, to duty cycle, like on and off, on and off, on and off, to fake it? This is what the OS already does, except he's not doing it within a JVM. He's doing it across processes. And of course, you can't run as root, so you can't actually have higher or lower priorities within a JVM unless you're willing to sort of commit suicide relative to other things on a box by lowering your normal priorities of a Java thread's normal priorities to something below the max that's the default for everyone who runs, so that your GC has the max that everyone runs at. What that means is if you run a lamp stack equivalent for the Java, you run a MySqueal with a JVM, the MySqueal will starve out the JVM's regular threads, right, completely, unless until the MySqueal decides he's done doing whatever cleanup he's doing internally. Your concurrent threads will run at max. They'll run the same priority process as the MySqueal. They'll be okay, but the Java threads will starve. Right, so it's an issue in production settings that are sort of reasonable setups. Alternative concurrency, we all understand, threads and locks and fast locks, but there's all these new concurrency ideas which I claim are useful and should be experimented with. And actors, message passing, Erlang, software transactional memory. Doug Lee's fork join I've done a lot of work with. It's really cool if it applies. People need a room to experiment above the JVM until we get some consensus on what the right way to do thread concurrency, right? The building blocks are there. The JVM provides some kind of building blocks, but it could provide other building blocks. Instead of locks, it could provide park and unpark. I don't know, people know what park and unpark is? Some people do, some people don't, it's fine. Specific kind of software transactional memory maybe would be another equivalent thing a JVM could provide as a building block to help you write a higher level of concurrency. Fixed nums. They're currently provided over the JVM. JVM provides int and long, but some languages want an idealized integer, which is an infinite overflow one, and the obvious translation to infinite math is fairly inefficient. Turns out that most hardware chips provide you instructions to do overflow math to support infinite precision arithmetic baked into the hardware, which you can't get at it from the Java layer or from the Java bytecode layer. There's no way to specify, hey, use a tagged overflow math here, which means you can't get to use the hardware that's there in the CPU to go do fast big integer math, right? Yeah. I'm not Bill Gates. So this one though is true. This is a pay-as-you-go kind of thing. You know when you're going to get overflow 64 bits. Okay, things to keep in the JVM: GCing, JITting, the JMM, and I claim that these things taken together mostly define what a JVM is. You have to have these deep hooks in the JIT process to support the JMM. Turns out you have to have deep hooks in the JIT process to support the GC. Turns out the GC has a really strong understanding of thread and thread models and thread concurrency, so it knows how to do incremental updates without breaking the Java memory model. And so these things taken all together are tied in a big-ass knot that I don't think makes sense to tear apart. There are some concurrency models, alternative ones. You might expose a weaker memory model, which could enable faster, cheaper hardware. The original Azul hardware, and I guess Itanium for the same thing, has a much looser memory model. Had Intel put the same kind of resources into an Azul box that they put into an x86, we would have much faster x86 chips, because the concurrency model can be papered over in the JIT process and be much simpler in the hardware side of things. It is what it is. Things that don't make sense in the JVM be the finalizers. Resource management of OS things. That belongs at the outside of the JVM. So the app needs to do a try resource, a lexical scoping, ref counting, some sort of lifetime management. But don't ask the GC that you can get more of resource X if I just run finalizers right now. Turns out for Azul, we did a lot of work in the incremental GC to aggressively find and execute finalizers incrementally under the hood to fix this problem, instead of taking sort of a blocking OS callback and a full GC cycle at a bad time. Same for weak soft phantom refs. If you have a cache, you want to have a caching policy, don't rely on the GC to do your caching policy for you. because the GC has no freaking clue that you have a cache or that it has a policy other than, I found a software, whack it. So, summary. Things to move out of the JVM into the OS, thread priorities, fast time access. OS resource management probably goes the other way. And some things that I claim applications do these days could move usefully into a JVM because it has access to better instructions or better JITting policies, better management of that kind of thing. Here's another one, Azul's GPGC does this aggressive virtual to physical memory mappings. IMMAP and friends are too slow. So we ended up doing, we got into the main Linux line, a user mode TLB handlers, which lets us, across processes, it's perfectly safe. But within a process, if I blow my TLB management, I kill myself, but that's my own bug. That's okay. But it lets me remap pages at terabytes a second rate. Hardware performance counters. JVM's already doing hardware performance, profile-directed compilation. He is already consuming all kinds of performance counters. Why can't I get the hardware ones and consume them as well? Turns out that you need to be root on x86 to get at the hardware performance counters. I don't know why Intel did that. But he's already, doing this mapping between perf counters and byte codes, and he's already JITting the code and managing it. At Azul, I gave you the mapping back from perf counters to Java through the bytecode layer, right? So I would like to see this exposed as a user mode thing on all modern hardware. Perf counters, they make better code. So move this mapping into JVM. We did this on the Linux for GPGC, not on, say, Windows or Mac. And hardware perf counters, which I have no idea why Intel just didn't make them user mode readable, but they didn't. And so you have to be root to go read those counters. And they're entirely useful for JVM. And the JVM is the natural consumer for perf counters anyhow. OK, basically, things you could do there. All right.
So, okay, thank you very much. If you want to answer the question, just hand up and I will give you a mic. So, okay, good.
Thanks for your talk. I wonder what JVM can do with megamorphic virtual calls. For example, you open IntelliJ IDEA, it does hundreds of inspections just for each of them and make virtual call and make hundreds, thousands of visit something to check your code.
So what I got out of this, what can I do with megamorphic virtual calls, right? In the land of, the Azul Zing VM, I could tell you what calls turned megamorphic and which ones were not from profiling. So there's sort of two aspects here. One is the Java level, I can do a reasonable analysis, like IntelliJ could do class hierarchy analysis. It does some anyhow, and tell you what can and cannot be based on just pure CHA megamorphic call. This call has no overrides, this call does. But when you run the program, there are many of those call sites will never go megamorphic. That class never gets loaded, the children below it never get loaded, the right combination never happens, this call site only takes this one kind of class, and you never go megamorphic. That thing IntelliJ doesn't have access to, but the JVM does. It's a perf counter, basically. So there is a way to go look at a running program and tell you which call sites went megamorphic and which ones did not. And the profiler, the JVM does profile, look at that, and having decided that you went megamorphic, if you went megamorphic on a small enough count, he'll start inlining the small count of things. So the obvious pattern here is direct byte buffers versus network byte buffers for NIO. The direct byte buffers are in memory, network ones are OS out of process memory that's shared with the OS doing network packets, basically jamming bytes in directly. So it gives you two targets, not one, that are common in all the hot inner loops moving bytes. Every possible place you do file.read.stream.read.write or whatever, all the I/O things, byte, 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 always a virtual call, always to one of two targets. The JVM knows there are two and inlines them both. Those are two and they're hot. So he's counting. But once you get past like 3, it doesn't make sense to inline them anymore. Now you just want to megamorphic call and go to it. And he can tell you which ones are which. And I don't know how to bring that information out so that an IntelliJ profiler could tell you what actually happened. That data is available. The Azul Zing VM would tell you it, but I can't give it to IntelliJ on an Oracle JDK.
Thank you.
No?
More questions?
Yeah, thank you very much for your talk. I wonder why didn't you tell about escape analysis? Because in my case, I actually work with markets as well, and that's pain in my neck. Data allocations where I can do nothing with. For example, var args or generics where you box as integers, just because that's JVM and you can you have to put integer in your map, and of course it will be boxing and
right.
Yeah.
Let's go.
Got the thing.
I got enough already. So escape analysis. It has a long history in the land of compilers. Various companies, IBM, well-known, well-respected for their compiler work, did an aggressive effort on compiler escape analysis. And the answer was always, it was too complicated to get any reasonable amount statically. You can't really catch enough of the weird corner cases to deduce enough stuff won't escape that you can usefully say, don't allocate. One of the things I did at Azul was I tried very hard to do an escape analysis that was escape detection, not analysis. I looked to see that an allocation did not, in fact, escape in practice. Just the same as you did with jitting, you had a de-optimization. I had a way to unwind my stack allocation and put it into the general heap, and it escaped, and that was an expensive path. But the fast path was you allocated on the stack, and then you deallocated on the stack using a lexical scope, and you had a test at the stack exit time that was cheap enough to say that it didn't escape, and done. Yeah, it's fine. I could get 60 to 70% of all allocations on a busy web server running stack allocated. It was not good enough to beat Azul's GPGC collector. So, that technology worked, but not enough to beat the Azul collector, but hugely beat the Oracle collectors of that date. Oracle get ZGC enabled, working well. Maybe it's less important. There's still a place now with the sort of the newer versions of x86, the cost of doing an allocation relative to the cost of your cores is high enough that maybe it becomes important again for performance, not because of garbage collection, but because of your cache footprint. I have an interesting talk on that maybe I could do at another time because it's not a short thing, but there's the cost of allocations much higher than people will acknowledge it to be. And in particular, things with very short lifetime that you allocate very frequently will not show up in your profile at all. They will not show up in your GC costs because your GC costs will all be young-gen, instant, microsecond level collections, be very quick. But you will be burning memory bandwidth like there's no tomorrow, and every possible thing that you reach for to memory will go to your caches will be missing because your caches will be flooded with new objects with very short lifetime. So everything just runs anemically slower. If you have hardware performance counters, it shows up. You get endless L2 cache misses. And you can deduce, you got high volume GC, high levels of things being allocated, high L2 cache miss rate, you're making junk objects at a super rate, you probably have a 10x speed up to be had by getting rid of the junk allocations, like a big speed up to be had. These days, you can't get that information out of a profiler yet, or you can with great difficulty. You have to go turn on like Intel's vTune and gear it up to the particular rev of the JVM. It's like a pain in the neck to get the right stuff out. There's some other red flags you can spot that's going on. The better answer is there's a coding styles that don't allocate once per X where X is very large. And you have to think about it. And like I had a class, I talk on this, it takes a couple hours to go through. But once you get it in your head, what's going on, it's straightforward to do, and then suddenly you get these big speed ups I'm talking about.
Good. We have several minutes for questions, so okay.
Thank you. The operating system can stop, interrupt a process at any time and any assembly instruction.
Okay, wait. Slow down because my Russian's really, really bad.
I'm sorry.
It's okay. It's okay.
The operation system can stop a process at any time.
Yeah.
Does JVM interrupt Java processes and how it works?
So you're talking about...
I mean optimizing code.
Yeah. Okay, and the optimized code. Okay, fine. So I'm going to there's a couple ways interrupts can be meant by what I heard. So I'm going to talk about the one I think that's not what you're talking about for 2 seconds. Hardware takes interrupts. The interrupts goes to OS. The OS has stopped your process at an OS level interrupt. This is not where I think you're headed. That just happens, and the JVM has no control over that. If you're looking for a very low latency garbage collection, JVM, say you're a low latency trader, high frequency trader, there are things you do to make sure that doesn't happen to your running JVM process by using like CSETs to lock down interrupts to different processes in the JVM. So there's that aspect. Coming around to where I think you're headed, it's you can run out of memory at any time. You can take a thread interrupt at any time. Like one thread can throw an interrupt to another thread. This thread can throw a thread.def at that thread, or a null pointer exception, or a range check out of bounds exception on that thread at any point. The debugger can interrupt you at any point. And how does that work in optimized code? Is that closer to what you're looking for? So how that works is there's this notion of safe points. And what's a safe point? A safe point is where the JIT has agreed that there is a mapping between the x86 instructions and the state of the Java of the JVM, the Java byte codes. So not Java, but Java byte codes. So there's a mapping. In between safe points, there is no such mapping. And the hardware, the JIT has reordered instructions. It has optimized things that wouldn't otherwise happen. It has made all kinds of fun assumptions, like I have this lock and I know I have it, so I'm doing lock-free games and I'm crossing locking boundaries and I'm doing all kinds of random things that aren't allowed. But then I get to the next safe point and I arrange that I match the Java memory model, the Java semantics, the JVM bytecode semantics of where it loads and what stores have happened. So anytime an interrupt would happen of the kind that you're talking about, GC, run out of memory, one thread throws an interrupt at another, or there's any sort of querying about the Java state, say from a debugger, you run to the next safe point, and then you stop. So there's a delay. And the delay is how long between safe points?
How many safe points are usually used?
Right. So that goes straight to the stall time between when one thread wants to do an allocation, it needs to start a GC cycle, and another thread is running to a safe point before you can begin the GC cycle, right? So there's a delay that some thread is doing some bulk work in a tight loop. He's not doing any allocation. He's just spinning, computing Mandelbrot's in a loop. I don't care what, something. And he doesn't need a safe point for any particular reason, but this thread wants to allocate, and he's out of memory. He has to run a GC cycle, and the GC can't start until this thread over here stops. And how long is that time? Okay, so there's two answers there. The first one is up to what I'm going to call counted loops. It's usually on the order of 1,000 clock cycles is the average time between safe points. The JIT does some. The JIT does not guaranteed put in safe points except at loop back edges and function calls, plus all slow paths that go in the VM, such as out of memory for GC. That turns out, in practice, to be on the order of 1,000 clock cycles, sort of the max normal kind of behavior. It will vary, depends code to code. Then there's a case of hot counted loops, which if you're running a low latency GC, you have to do something about, but if you're running an Azul collector, you don't. Azul, sorry, you're running an Oracle collector, they didn't. And that is a hot counted loop. That is one where I know the bounds is finitely trip counted and there's no allocation going on. There's no other reason to have a counted loop. If the loop's small enough, that safe point overhead, the cost of bringing yourself to a valid known Java state can be double or triple the cost of running the loop. So I voted them out 15 years ago. And you could have a long-running loop over a big array that won't take a safe point until it exits the loop. For Azul, to get to a low-latency collector, we did a compiler optimization called Unrolling Jam, where you unroll the loop body enough times, and you do an inner unroll that's big enough to mini-batch your way efficiently, but then you do a safe point every 4 or 10 trip counts through the loop, but the loop's tight. You didn't bother to do this until the loop was tight, because the safe point overhead's small if the loop's big. So if the loop is tight, you unrolled it 4, 8, 10 times, then you took a safe point, but then you did that in a hot loop, so you got a safe point every 8, 16 trip iterations. And I don't know if Oracle ever got around to doing that, but if they want to do a really low latency collector, they're going to have to.
Thank you. May I ask you yet another question? In my opinion, JVM or libgc JIT isn't a real JIT.
I'm sorry, if what? I heard GPGC?
GCC.
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 Yeah, okay.
Has a library for JIT comparison too.
Yeah.
But it is very simple JIT
Yeah.
without the optimization, profiling, and other things.
Right.
On the other hand, there are many projects, Java, JVM, Coronet, Firefox, Chromium, Mono, with JIT compilers. So, is it possible at all sufficient points of view to develop an open source library for JIT compilation? Why not? Why yes?
So Firefox and Mono and let's break things out a little bit differently here. Firefox is a browser. It's running JavaScript. So you're actually talking about a JavaScript compiler.
Yes.
So JavaScript has a very different compilation target than Java. So they both say Java in the name, but that was just an accident of history, right? The actual programming language, for instance, has no types. It's dynamically typed. It has types. It's dynamically typed, which means that in order to discover types, to do the kind of optimizations that the Java compiler does, you have to do all kinds of dynamic analysis profiling, which all the modern JavaScript JITs do. So what I heard you ask is does it make sense to do one for open source? Yeah, sure. And I would think that there's such things floating around. Is that going to stop Google, V8 and Microsoft's, what's the Microsoft one? There's a good one from Microsoft too. But there's these things floating around that big companies are pouring huge counts of man hours into to make them go well. Are you going to catch up to them from your open source project? Probably not without similar level of resourcing. Can you get close enough that people are interested in using it? Maybe, but only if I'm not running on Chrome or Firefox, which I already get the right good, JIT compiler for JavaScript. Now, if I'm interested in compiling other languages than JavaScript or Java, but I want a JIT compiler, then you have the problem of doing a language translation in a compiler separate from the runtime aspect. So it's been the case for many years that compilers aren't actually truly multi-language very well, because different languages have different kinds of things that are important to optimize for and different kinds of program semantics that don't transliterate well to other languages. So we're a little better now than we were 20 years ago, but it's still a pretty rough space to be in. You'll have a kind of an average meh compiler for all possible different languages, rather than a great one for Java and a great one for JavaScript. That happens. Separately, there's the runtime issue. And again, the runtime semantics are a giant difference between the different languages and the different use cases of how they're done. Some of that can be commonly pulled in. Grab the hardware performance counters, mapping it back to your underlying representation, whether it's JavaScript or Java Byte Codes or whatever it's going to be, and then using that in the JITting process. You'd love to have that work. You need to know about hardware level exceptions, because you want to do null check elimination by using like memory ops to do the null check for you. You still have to take the null check exception, catch it in the hardware, map it back through the OS into your process and decide you took a null check here and deal with it however that semantics go. So you're taking hardware interrupts, you're taking TLB pages, you're taking hardware performance counters, you're taking core semantics, the memory model between multi-core systems, and trying to put them together that will work for all possible languages. Like, JavaScript's really a single-threaded language. What's the multi-threaded semantics for JavaScript? Well, the Node.js people are still wrestling with that one, right? They still want to have this notion of a node server, have all these independent JavaScript threads running. We're sharing a code cache. That's great. We did it only once here. But we want to share database lookups. We want to have cross-thread communication on who can put things into the cache or pull something out of the cache. And what's it mean to put something in the cache where I'm writing byte after byte after byte in the cache and somebody else wants to read. He gets it out of order with I'm still filling the cache. So he maybe gets only half of it and then he crashes and burns because he didn't get the whole thing or whatever. So he has to have a program language semantics model. And there isn't one for JavaScript. There isn't one for PHP, right? There isn't one for a lot of these languages that are intended to be sort of single-threaded, easy ways to talk about web services of various kinds. You have to invent one. Same with Python. Python's in the same boat here. The cross-thread communication is I called a C library routine, and it did something cross-thread inside the library routine, did BLAS routines in the library, and then it came back to my single-threaded Python code. So can it be done? Maybe. Is it worth it? Maybe if you did it well. Is it a lot of effort? Yes. Oh my freaking God, that would be a huge amount of effort. I would love to say that there was a long-standing, large, well-funded community that people believed in, ECMAScript or something, building an alternative to whatever as an open source library. Do I see that today? No, I do not. I'm sorry? I have been in contact with the GraalVM folks for a very long time. I would claim that they're just now getting close enough that it matters. They have been playing catch-up on the asymptotic curve to the hotspot VM for 20 years. And they weren't ever, like 5 years ago, they got where they could run the common benchmarks and get similar numbers. But if you're tying to the industry standard and you're not beating by substantial amount, who cares, right? Graal, G-R-A-A-L. They've done a good, useful thing. They basically rewrote the JITting process in kind of a Java-like thing, but they rewrote from scratch, whereas the compiler I wrote was in C code, C++ code, 25 years ago, and I did the right things at that era, at that time, with the tools I had in the place, right? And you could argue that 25 years is a long time, and a rewrite we're due for, and life could be better. Okay, but like I said, they've been playing catch-up, and they haven't really exceeded. They have exceeded in a new domain, which is where you might get some traction. And that is they went ahead and did the cross JVM to native code, C code, boundary in the compiler so that you can cross that boundary much more efficiently in Graal than you can in Java. And I have a separate talk to go about there, but to do it in Java the way it's done today, without the JIT process involved, every crossing between Java code running JVM byte codes that are JITted into C code carries an overhead of 50 to 100 clock cycles, which if you're doing a database call, you don't care. It's like, I'm going to do a billion cycles anyhow, I'm waiting for a disk, I don't care. But if you're doing it for something really cheap because you want to get a video codec, something that's going to be really fast, use custom assembly instructions to go process audio or whatever and come right back, 100 clock cycles might be more than that cost of that call, and you want to make that boundary efficient, right? So there is a use case there that's available. Same crossing might happen for doing graphics on my phone, right, and video games, right? Speech recognition, right? Video recognition where my phone looks at your face and tells me your name because I'm horrible with names, and I'd love to have the thing that like popped up and gave me your name, whatever, fine. Okay, there are places where this could be useful. So I don't claim Graal's dead by any means or has no chance. They need to push their strengths, and the market as a whole needs to discover the strengths and believe that strength is important, and then they'll get pulled forward. As it stands now, they're getting pushed from behind to try to catch up to the leader, and they're basically asymptotically getting closer and closer, but they're not really ahead of the leader. They're kind of on par unless you're in this other space. If they get something better going with escape analysis, maybe they could pass the leader on sort of raw performance. That'd be good. So where they stand now, they've worked 20 years and they've hit a tie. That's not good enough. But if they get 10, 20% above on every day, every month's regular Java code, I think people would start flipping the switch. You know, it's a new technology, it has its new issues, it has bugs, it has performance holes where it worked and it crashed, or it ran really slow and it ran fast, and you don't flip that switch for free. You know, if I'm running my business on this shit, I'm not gonna throw that switch until I know it's solid. Same thing happens for GC. Watch Oracle's history of flipping GCs from the default, right? It takes a very long time for them to get stable and reliable enough that people will bother. I still run all kinds of shit on the old school collector because I know its performance profile, I know how it works, and for what I do, it works really great. CMS was forever this like horrible thing. G1 is still not close to the Azul collector. ZGC might catch up to the Azul collector at some point and be good enough that people will en masse really want to flip that switch. I'm just saying, there's a long curve ahead. They're not there yet. They could yet get there, but they should push their strengths and go to places that the current compiler really isn't going to ever go. And that's how they'll carry the day.
So if my understanding correct, Gradle, they used C of nodes?
They use what?
C of nodes?
Yeah, they use the same compiler technology.
That's very interesting because like about 20 years between them, but still the same technology.
So
what do you think about this?
I did the C of nodes sort of on my own back in my grad school days. And you know, for me, it was just like an obvious thing that kind of like fell into it. And over the decades, I've seen no more than half a dozen people considered as a viable compiler technology. But everyone who uses it just loves it to death. And it does something really magical for the ability to talk about program semantics. The Gall folks didn't come from a C of nodes background, but they saw what I was doing with it and why it worked, and they like it for the same reasons that I liked it. It's a strong, good way to do compilers. It's not necessarily the standard one you get out of an academic instruction setting. You won't get it a class taught at. You take a compiler class, you won't get it. But in my opinion, it is the right way to write a compiler.
Okay, but do we have some alternatives for C of nodes? So do you know something about it?
Alternatives to C of nodes? You mean the existing academic way people do compilers forever and a day, or
so probably both academic
open source?
And practice. No, not open source, but maybe in academia or in practice.
So academia, you do a different thing. You do multi-layer graph of control flow graph, and then a list of instructions in a basic block. You have tuple versions of the same thing. Then people pile on SSA form for some pieces, and then they back it off, and they compile on SSA again, they back it off, and they do some stuff, and they run wave after wave after wave after wave. And what I can do in C of nodes is I'm basically permanently in SSA form all the time, and all the wave after wave after wave passes become incremental, truly incremental. So you lower the big O notation of the running time for all these algorithms. So everything is done on the C of nodes, and everything is done as a graph rewriting rule on the C of nodes, and you drop an order of magnitude in execution cost. And the actual optimizations, because it's this graph rewriting rule, once you wrap your head around it, it's like really easy to define a new rewrite rule. The rewrite rules are, here's my prefix, here's my transform. And then the system just applies the rewrites one after another incrementally until it's done. And that's your optimized program. I'm being a little naive there, but that's the bulk of how that goes. Actually talking about C of nodes as sort of an open source thing, it's such a simple concept once you finally get your head wrapped around it. I don't know that it needs a framework that you just custom write your own. It's not very hard to write a C of nodes system once you get your head wrapped around what goes on there. There's a very simple transliteration in your brain, and then like, oh, I get it, and then suddenly the semantics are all obvious, and now how to build it becomes obvious, and how to use it becomes obvious, and all that kind of stuff. So, I don't know, maybe talking to the wrong audience. That's a different talk.
So, probably, what do you think about Falcon compiler from Azul?
I left Azul a while ago, and they're going to do what they're going to do. As far as I know, they're in business to do, low latency GC is sort of the main thing, and they have a slick profiler. How they JIT code is their business. Okay. I'm not going to make a judgment call on what Azul's business choices are.
I have a question. Cliff, thank you very much for your talk today. I wonder, what's your opinion about current state and rate of innovation across JVM and other technologies? I would say, well, Google, for example, made V8, and there's a huge business now for JavaScript on server side, and Google Go. It's not JIT compiled, but they do have GC. So what do you think? How do these modern technologies compare? And what's the trends here? I mean,
right.
Yeah.
Okay. So Java's still here. JVM's still here. JVM's going very strong. So people are voting with their feet, right? There are things for which Go makes a lot of sense, and there are things for which Go looks like an interesting alternative. And there are people who just want to be different. And they'll use Go instead of Java because it's different. And I look at the technologies baked into Go, and I claim that if you just thought cleanly about how you write Java code, you'd get 80, 90%, minus maybe Go routines, which add a new twist to how to do concurrent algorithms, for which JVM's kind of locked into doing threads and locks style. You add a library to do Go routines in Java, you totally can do that. It won't be as convenient to use as Go routines because you have to make a library access instead of directly using the things, right? So there's a call to be made as a specialized, like Go routines apply to my use case, makes sense to use Go. As for the compilation technology, they're missing a profile-directed compilation. So they can't get that piece. They can't lazily add code later. They can't do a bunch of things that are actually fairly tricky to get right, but once you get the right, there's a nice payoff behind them. So there are some hard problems they didn't solve, and as a consequence, they don't get the gains that come with solving the hard problem. And that sets their direction of where that technology is applied. I don't think Go will replace Java as a mainstream large use case anytime soon because they are not solving those problems.
What about V8 on the server side? This is JavaScript,
right. So JavaScript's gone a little different direction. They kind of went after everything that Java stood for minus strong typing. So skipped strong typing. They got aggressive JIT compilation. They got aggressive GC. They have a desire to run these things. They actually are running multi-threaded. They're trying to hide it from you. They don't have a good multi-threaded story, but multi-threading for independent things. They do well multi-threading for independent things, which is the thread pools work list kind of model does okay. You get a new JavaScript thread every time a new web page or new tab, right? If you're doing other kinds of work, it becomes more difficult to do multi-threading without having a memory model of how people talk. In particular, I mentioned you want to cache. You want to cache database lookups, for instance. There's a lot of other things you want to cache. The Node.js will cache JITted code for you behind your back, but they won't cache database calls. So you have to have something that does that. And for some of these things, there are people have argued or fought and made custom hooks that add caching. But as soon as you're outside the domain of I just want another cache, you don't have any way to go parallel JavaScript. And that turns into, I don't know how to write a multi-threaded JavaScript program other than one that's doing independent tasks that's sharing a cache. There's a big use case there, but it's not the whole world of things to go do. So I think JavaScript has got legs, not just because of the World Wide Web, but because it's a useful programming language that tackled some of the hard problems that Go's just dodging. I don't think JavaScript will go away anytime soon. I think it can't achieve Java's performance because they don't have types in the language. And that means that no matter how much profiling you do, in order to have the correct semantics, you have to have backup tests everywhere that just eat into your performance, and that turns into the 30%-ish that JavaScript runs behind Java. Java's running C code speed. JavaScript is not, but it's close. 30% is not too bad. Python's 10x slower. Python folks are just like shooting themselves in the foot, I guess, bang. Because they could go a lot faster, but they just haven't decided they want to bother. They've basically shot down all attempts at running Python JITted by making it difficult and not having any flexibility at all about how you execute or think about Python. I think that's a mistake on their part. It's a great scripting language. As soon as you go production, you hit some small threshold and you switch languages immediately because it's just too slow. Nice for exploratory work with data science. As soon as I have a terabyte data set, it's too slow by orders of magnitude. I'll never do it. Whereas I can run Java on a terabyte, do logistic regression in a minute, on a terabyte of data. I can't even load a terabyte of data in my Python. The JVM, the Python VM will crash. It's just like, nah, it doesn't work. Oh,
Thanks a lot.
yeah.
And probably the last question for today.
So just to be clear, I haven't had dinner yet. I'm going to go to dinner after this. If people want to join me for dinner, that would be fine, and we can carry on the conversation at dinner. But I'm ready for dinner and a beer.
Thank you very much for the talk. My question is about biased logs.
I'm sorry?
Biased logging.
Biased locking, yes.
Isn't it an obsolete concept nowadays? I mean, cache is pretty fast now, and biased log gives a small benefit when it works, but when it doesn't work, it has a terrible overhead. It can stop the world pauses for hundreds of milliseconds.
Right. Okay. So Azul did it cheap, and so it works great on Azul. And that goes hand in hand with all that giant rewrite of the core JVM infrastructure that Oracle never did. So Azul can stop an individual thread on a nanosecond boundary, more or less. Yeah, microsecond boundary, whatever safe point pauses on an individual thread. And that's what you need for bias locking. This thread wants to lock, this thread holds it biased, but isn't at any safe point and is just running freely along. This thread can stop this thread and no other thread at the next safe point for this guy, a clock cycle to do a store, and for this guy, a clock cycle to do the load, compare, and oops, I have a safe point. And then he does a self-service task, which is, I have to release the bias lock. I have to go count. How many times do I actually own the lock? Do I still own it legit or not? And if I don't, release it. He does that all hot in his L1 cache, and he's done in microseconds or less. Gets down to like the 1 microsecond range, and the lock is released. So it can be cheap. Now, CAS got cheap about 2012 for Intel. It went to L2 cache hit, be a dozen clock cycles on a 3 gigahertz processor. It's not too bad. And so you could just CAS in and CAS, except you lose the opportunity to kick the JIT in across the locking boundary. So one of the other things Azul did was what they said, if we were going to be bias locking here, we had that into the profile counters. The JIT comes along and says, this lock's being taken biased. I will widen the locking border to the width of the JITted compilation unit and just test the bias up front, and don't have to do anything on exit if I got the bias up front. In the middle, there's no locking boundaries. And if there's no locking boundaries, then all code scheduling can cross all locking boundaries, and you get that level of optimization too. So you get more performance than just, I didn't pay 10 clocks in, 10 clocks out on a CAS. You also got whatever you got for crossing locking boundaries. That varies by the code and the nature of how it's being used, but it can be, dozens to thousands of clocks. It could be nothing, it could be 10%. Depends on your coding style there. So, and there is a way to go forward. Oracle needs to fix their threading internals, and then there's a way to make bias locking really cheap.